Hello, I am Maria Luis Puertas and I'm talking about the mean plus matrix product for large matrices, sequential versus parallel implementation to compute domination type parameters in cylindrical graph. This is a joint work with Garzón, Martínez and Moreno, and we are from Universidad de Almería. So first, I will present the definition of some domination type parameters in graphs and also the Cartesian product graphs. And then I will show how algorithms using the mean plus matrix product can be used to compute this type of parameters, and also the computational requirements of such algorithm in both sequential and parallel implementation. And finally, I will talk about the result we have obtained and also the work that we are doing at the moment. So, first, the domination number of a graph. A dominating set in a graph T is a vertex set such that every vertex not in it indeed has at least one neighbor in it. And the domination number, which is called gamma of G, is the minimum cardinal of a dominating set of G. You can see here a couple of examples. On the left, the set of black vertices is a dominating set with 3 vertices, and it is not minimum because on the right you have another example, again the set of black vertices, which is also a dominating set in the same graph, and it has 2 vertices. In this case, it is a minimum dominating set, and the domination number of this graph is equal to 2. You can see here a general reference about this topic in graphs. You can find in the literature a lot of variation of this definition. For instance, the 2 domination number. A 2 dominating set in a graph T is again a vertex set D such that every vertex not in D has not just one but at least 2 neighbors in it. And the 2 domination number, which is called gamma 2 of G, is the minimum cardinal of a 2 dominating set of G. Again, a couple of examples. On the left, the set of black vertices is a 2 dominating set with 4 vertices, and it is not minimum because on the right you have another example. Black vertices again is a 2 dominating set. Note that each white vertex has at least 2 black neighbors. Indeed, the white vertex on the bottom line has 3 black neighbors. In this case, it is minimum, and the 2 dominating number of this graph is 3. You can see here a paper of 1985 with where you can find the definition of this parameter for the first time. And now the Cartesian product graph. The Cartesian product is a graph operation, a typical graph operation. If you have 2 graphs, H and G, the Cartesian product of them is a new graph with vertex set, the Cartesian product of both vertex sets, and such that 2 vertices are adjacent if and only if the first coordinates are equal and the second ones are adjacent in H, or the first coordinates are adjacent in G and the second ones are equal. The graphs we have seen before are both Cartesian product graphs. In the first case, we have the Cartesian product of 2 paths, which is called in general a grid, and the second example is the Cartesian product of a path and a cycle, which is called in general a cylinder. In general, domination type parameters are difficult to handle in Cartesian product graphs. Several parameters of this type have been computed by using algorithms involving the mean plus matrix product in both grids and cylinders. This matrix product is defined over the semi-ring of the so-called tropical numbers, which is a semiring with set real number union infinite and operation minimization and addition. This matrix product follows the same structure than the usual product, but changing the addition by the minimization either and the product by the addition. So with this matrix operation in this paper of 1996, the author presented algorithms to compute the different domination type parameters in Cartesian product graphs. I'm showing a sketch of how these algorithms work. For instance, in a cylinder, you have to fix one factor with a small size, either the path or the cycle. In a first step, you compute the domination number of the cylinder with this fixed factor and also the other factor small. And in a second step, if you fix the path, then you can compute the domination number of the cylinder PNCM with this fixed path Pn and any cycle. And if you fix the cycle, then you can compute the domination number of the cylinder with such a fixed cycle and any path. The general case, that is the domination number of a cylinder with any path and any cycle, was partially obtained in this paper of 2020 and uses the information of these small cases, but moreover requires additional techniques to obtain the general form. The two-dimensional number of cylinders is unknown, and here we complete steps 1 and 2 for this parameter and following similar ideas. That is, we compute the two-dimensional number of a cylinder if either the path or the cycle are small. We would like to point out that this is the starting point to solve the general case, because the general case needs the information of these small cases. Our algorithms works in the following way. Remember that you have to fix one factor. So if you fix the cycle with a small size, then each two-dominating set is identified with a particular labeling of the vertices. The labeling provides a matrix A and a vector x1. Then we can compute a sequence of vector x2, x3, and so on by multiplying with the mean plus matrix product the matrix and the vector. And then for the step 1, that is n, the path is also small, the vector xm gives the two-dimensional number of the cylinder PNCM. And for step 2, the sequence of vectors x1, x2 until xn0 for a suitable n0 provides a finite different equation that gives the two-dimensional number of the cylinder PNCM with cycle Cm fixed and small enough and any path. In the other case, if you fix the path with a small size, again each two-dominating set is identified with a labeling of the vertices which is different from the previous one. This labeling provides a matrix in this case, and we compute a sequence of powers of this matrix using the mean plus matrix power. And for the first step is n, that is the cycle, is also small. The power an gives the two-dimensional number of the cylinder PNCM. And for step 2, the sequence of matrix powers a squared until a to n0 for suitable n0 gives in this case a finite difference equation that provides the two-dimensional number of the cylinder PNCM with a path fixed and small enough and any cycle. And now let's talk about the computational requirements of our algorithms. In the case that the cycle is fixed, we have to compute one matrix and several vectors. Both the matrix size and vector sizes exponentially grow with n, and this is the reason why we have to consider just small cases of the size of the cycle n. Both the matrix and the first vector are sparse, however, the sequence of vectors are dense from the third or the fourth one. We have to compute the mean plus matrix product of a matrix and a vector. In this table, I'm showing the results in cases of n between 3 and 15. We have the memory sizes for these cases, and also we can see that the most consuming time process is the computation of the matrix A. In the largest case, that is n equal 15, this part took more than 8 hours. However, the computation of the sequence of vectors with 20 vectors in these cases took around 3 hours and a half. And what about the other point of view? If the path is fixed, then we have to compute powers of a large sparse matrix. In this case, also the matrix size exponentially grows with n, and again this is the reason why we have to consider just cases of n small enough. As I said, the matrix is sparse, however the powers are dense from the fourth one, and we have to compute the mean plus product of two matrices. So we tried the same idea as the previous case, a SQL implementation, and we did the cases with n between 20 and 12. So you can see here again the memory size and the computation time of the matrix A. For the largest case, n equal 12 is not a lot, it's just 4 minutes. However, computing the sequence of matrices with 50 powers in this case took a lot of time, and the largest case we did here is n equal 10, and we needed more than 33 hours to obtain the complete sequence. So this is why we thought that would be a good idea to try a different approach. So we tried the OpenMP parallel implementation with 48 threads, and here you can see the comparison between both implementations, the sequential and the OpenMP parallel. You can see the speed up is not a big deal for small cases. However, for cases 7, 8, 9, and 10, you can see that the speed up is increasing. And in the largest case that we did with both methods, which is n equal 10, we needed 33 hours in the first case, but just 1 hour in the second one. With the parallel implementation, we were able to finish the following case, which is n equal to 11, and it took 16 hours. So this is why we are now trying a different approach, and we are working in a GPU implementation of these algorithms in order to be able to do larger cases, case n equal 12, and even larger cases of n. I would like to finish summing up our results. So we have obtained algorithms to compute the true termination number of a cylinder such that one factor has a small size, the path of the cycle, and we use the mean plus matrix product in our algorithms. And with sequential implementation in a CPU, we can compute the two-domination number of cylinders with cycle between 3 and 15 vertices and any path. And with an open NP parallel implementation, we can compute the two-domination number of cylinders with paths between 2 and 11 vertices and any cycles. And at the moment, now, we are working in a GPU implementation of our algorithms to reach the computation of larger cases. And from the mathematical point of view, the values we have obtained for the two-domination number of a cylinder with a small path or a small cycle give us the opportunity to observe a regular behavior in the cases of cycles with size congruent with 0 modulus 3. And moreover, this regular behavior gives not just the number, the value of the two-domination number, but also the construction of a minimum two dominating set in such particular cases. This regular construction can be extended to any size of cycles in the case n congruent with 0 modulo 3. So we obtain this upper bound for the two-domination number in such cases, which is n times n plus 2 over 3. At the moment, we are working in the general case, starting with this case. So our first goal is to prove that this upper bound is indeed an equality and this is the real bound. That's all. Thank you very much for your attention.